All right, thanks, Terry, for the introduction. Good morning, everyone. I should specify I'm an employee of GE Healthcare. So this work is motivated by the fact that there are a number of challenges in using a gradient echo API sequence in fMRI. First and foremost is it's very loud. Not only does this make the experience very uncomfortable for subjects, but it's also been shown to modulate resting state networks as well as even task-based results. There have been some efforts to reduce mechanical vibrations of the gradient coil with either sinusoidal or spiral gradients, and they've achieved about a moderate 15 dB reduction in acoustic noise. However, they have long readouts, and so they suffer our second problem, which is spatial distortions and signal dropout, especially at 7 Tesla. Now, this is obviously a problem in your analysis, but you can solve this if you use a shorter acquisition like a GRE based with a T2 prep. However, it's going to be extremely loud, like our first problem. And third is specificity. So gradient echo API is sensitive to T2-BOLD, which means you're going to have contamination in your BOLD activation patterns from the large draining veins. What you really want is your signal to come from the capillary bed, which is close to the site of activation. And you can get that contrast if you use a spin echo API. But again, it's going to be loud, and you're going to have some spatial distortions at 7 Tesla. So the goal of this talk and of this work is to try to address all of these challenges in a single sequence. Now, the basis for this sequence is something called 3D radial ultrafast imaging. Now, the 3D Rufus sequence, each acquisition is composed of 3 parts, a very short high bandwidth RF excitation, followed immediately by the radial readout of an FID. After that, there's a very small gradient update which perturbs our position in K-space and gets us ready for our next acquisition. And in so doing, we can fill out our K-space volume with these radial projections. And if you follow that dark blue line, that's essentially these gradient updates throughout the volume. So they're very smooth. Now, because this is an FID acquisition, it's 0 TE, meaning there's a 0 echo time. So there's going to be no spatial distortions or signal dropout caused by T2 star dephasing. Because each of these acquisitions is on the order of a millisecond, it's very high encoding spatial efficiency, allows us to acquire 3D volumes in a matter of seconds. And because these gradient updates are very small, it's not switching back and forth like an EPI readout, it's virtually silent with no eddy current distortions either. However, because these acquisitions are very short, and because it's 0 TE, it is mainly a proton density weighted contrast. So to use this for fMRI, we can add a T2 prep module prior to the Rufus readout, and the T2 prep is essentially going to give us a spin echo-like contrast. But with the Rufus readout, meaning we're going to be distortion-free with no signal dropout and very quiet. To prevent T1 contamination throughout the volume, we use a segmented approach. So we have basically 2 segments. Each segment is preceded by the T2 prep, and this allows us to get 3 mm whole brain coverage in under 2 to 3 seconds. And because we need Cartesian volumes to analyze, we can reconstruct these volumes using iterative sense with a total generalized variation regularizer. So this work has previously been shown at 3 Tesla, and you can see here in the top left a comparison of the 3 main techniques of gradient echo, spin echo, and T2 prep Rufus to a high bandwidth SPGR spatial reference. Now we can essentially assume the SPGR has no spatial distortions or signal dropout, and so in comparing that to the EPI-based acquisitions, you can see there's large distortions above the sinus and around the temporal lobes. However, in comparison to the T2 prep Rufus, we see none of that. Now looking down at the acoustic noise table on the bottom left, we can see that the ambient room noise of the scanner room is about 72 dB, and the EPI-based sequences are roughly 40 to 142 dB higher than that. However, the Rufus-based sequence is only 2 dB higher than the ambient room scanner noise, which means it's achieved a 40 dB reduction in acoustic noise in comparison to EPI. Now, if you look at the motor and auditory task results, we can see the sequence is sensitive to T2-BOLD contrast. However, that sensitivity is only about 1.5%, which brings us to why we're going to 7T. Essentially, 7T has a higher intrinsic SNR, which should increase the T2-BOLD sensitivity of the sequence while maintaining its distortion-free nature and low acoustic noise. However, in moving to 7 Tesla, we need to be wary of how we do the T2 preparation. If we basically just take this standard MLEV T2 prep, we'll have a lot of RF artifacts in areas of high B0 and B1 inhomogeneity. So we've chosen to use what's known as a Burr4 pulse for the T2 prep. And the Burr4 pulse is B1 invariant and also allows a high bandwidth for B0 inhomogeneity. It's adiabatic and is segmented, so it allows you to do variable effective TEs. For 7 Tesla, we've chosen 50 milliseconds. And if we take a look at the kind of contrast you can achieve with this pulse, we used it in a T2 prepped MP range at 7 Tesla. You can see the contrast is actually very flat throughout the entire brain. There are no RF artifacts above the temporal lobes or the sinus or the cerebellum, which are typically problematic at 7 Tesla. So to test the T2-BOLD sensitivity of the sequence, we ran a number of experiments, the first of which was a left-hand motor squeezing task on one volunteer. The task consisted of 15 seconds of rest, 15 seconds of movement for 9 cycles. And we had our subject repeat this task during the Rufus sequence, spin echo EPI, and also gradient echo EPI. Now, all the sequences were TR matched at 3 seconds and spatially matched at 3 millimeter isotropic whole brain coverage. However, the spin echo EPI, since it's SAR limited, we were only able to get down to about the midpoint of the cerebellum. The data was analyzed using the GLM and FSL. For the resting state scans, we performed those on 7 volunteers with eyes closed. Again, for the 3D Rufus and the gradient echo EPI acquisitions. They were TR matched at 2.6 seconds and spatially matched at 3 mil isotropic whole brain coverage. We analyzed the data using FSL to do group ICA and register them to the MNI space. So we can see here a comparison of the distortions and signal dropout to a spatial reference, an MP-range spatial reference. And we can see here, looking at the EPI-based sequences, that there's significant dropout above the ear canals at the ear tissue boundary and spatial distortions in the frontal lobe in the gradient echo EPI. However, in comparing that to the T2 prepped Rufus, we see there's no signal dropout above the ear canal, nor are there spatial distortions in the frontal lobe. So it is actually a very robust sequence at 7 Tesla. So in looking at our task results, we see the expected contralateral BOLD activations in the right primary motor cortex in the gradient echo EPI, as well as in the spin echo EPI. Although you can see the spin echo EPI, because it's T2-BOLD sensitive, is going to have a lower sensitivity than the gradient echo EPI, but is also more specific to the gray matter. And we compare that to the 3D Rufus results, and we see the 3D Rufus results are actually very similar to the spin echo EPI as expected. However, the sensitivity is just slightly lower, and we're trying to figure out if it's because the spin echo EPI does have a little bit of T2 star contamination in it from the EPI readout, and the 3D Rufus is pure T2, or is it because the 3D Rufus protocol is simply not optimal, and we're just losing some sensitivity there. Now looking at the resting state results for the 3D Rufus acquisitions over our 7 subjects, we can see that there are some group ICA components that are similar to known resting state networks, the top being the default mode network, the middle being the primary auditory network, and the bottom being the sensory motor network. So we can pull networks out of the resting state scans with a 3D Rufus sequence. So in closing, the sequence does achieve each of the stated goals. It is very quiet, it's distortion-free with no signal dropout, and is sensitive to T2-BOLD contrast, as evidenced by our experimental results. We're able to achieve whole brain 3 millimeter isotropic coverage in about 3 seconds. And this should enable new auditory experimental paradigms and increase access to subject cohorts, such as people with anxiety or autism who cannot be scanned by a loud EPI acquisition. And it should also simplify the study of different regions of the brain with high B0 homogeneity at 7 Tesla. Now, I want to emphasize this is not a replacement for spin echo EPI. The sequence is both spatially and temporally limited in comparison. We view this more as a complementary technique. But that doesn't mean we don't want to try and improve the spatial and temporal resolutions, which is something we're looking into right now. And part of that is going to be redesigning the T2 prep pulse. BER4 pulses tend to be very high SAR, and so it's preventing us from removing or reducing the TR even further. And of course, you want to try this experiment, this sequence, additional auditory experiments, which have not been possible with the high background noise of EPI scans in the past. If you want to learn more, please come by and talk to me at poster 1789 later today. Thank you.